back for another video made just for the folks in STOR 155. This video is going to talk about section 5.3 on hypothesis testing. And the first thing I need to do is revisit a point or two that I made yesterday when we were talking about those adults in Turkey. There's one subtlety that I didn't draw your attention to, and that's that recall that we knew that the average caloric intake for adults in Turkey was 3,500 calories per day, and we were interested in this subgroup students at Ankara University, where we took a sample of 25 randomly selected students, and we got that their caloric intake was 3,400 calories per day. And I want to be clear, the question we asked was, is there enough evidence to conclude that Ankara students average less than 3,500 calories a day? And this is not sort of the most natural question we should ask. Usually we just ask is this enough evidence to decide that Ankara students have a different caloric intake than the rest of Turkey? But I want to remind you that in this case, where I specified less than, we ended up with a null hypothesis, and I'm going to talk more about null hypothesis today. But our assumption without other information is that the whole population, mu for the population of all Ankara college students, should be the same as for all adults in Turkey. So our null hypothesis, or our assumption without evidence, is that mu is 3,500. And our alternative hypothesis, since I specified less than, is that mu is less than 3,500. Okay. All right, so just as we do another example in a minute, I want you to recall that. Okay, so today I want to ask a similar question. I toss a coin 100 times, and I get 64 heads and 36 tails. And the number of heads is 14 away from what we would expect. So I didn't specify less than, anything like that. And I just want to know, is this enough evidence that the coin is not fair? Okay, so fair coin. This is going to disappear on the next page, but I just want to say fair coin means probability of heads is 1/2. Okay, a coin is not fair, so not fair, if the probability of heads is not equal to 1/2, so not greater than or less than, but not equal to. This is going to be called a two-sided hypothesis test, which is coming up in a few slides. But so H0 in this case would be P equals 1/2. The alternative hypothesis would be P not equal to 1/2. I may have just said H equals 1/2. I meant P equals 1/2. Okay, so we can clean this up and look at the next line. So we got 64 heads, and this may cause us to be suspicious that our coin is not fair, but it might have happened by chance. Okay, there are two possibilities for why we got a number of heads so far from 50. Either the coin is not fair, okay, or we got 14 away from what is expected just by chance with a fair coin. And to decide which is the case, we always find the probability that this result happened by chance for a coin that fits the null hypothesis. Remember, the null hypothesis is that P equals 1/2. Okay, so in this case, we're looking for the probability that the number of heads, let's call that X, that X is either greater than 64, or, since all we're interested in for the alternative hypothesis, so I'm writing way up here in blue up here, since it's P not equal to 1/2, I'm just interested in the fact that I'm at least 14 away from what I expect, okay? So that's the probability that X is greater than 64, or X is less than 36. And you may say, hey, wait a minute, I saw 64 heads here, why don't I just deal with greater than 64, like the example with Turkey? Okay, and the reason is we do a two-sided hypothesis test. Unless we have a reason before we look at the data, unless we have a reason to believe it should be lower or higher. Okay, in fact, many statisticians would say you never do a one-sided hypothesis test when a two-sided test makes sense, when it's reasonable to do a two-sided test. So with the example with Turkish caloric intake, we should assume that there was some reason to believe Ankara University students had a lower than typical caloric intake. Okay, so we're interested in the probability that X is greater than 64 or less than 36. It says at least this far away. So 14 away from what is expected. So I should probably say greater than or equal to 14, less than or equal to 36. We would find this probability with a binomial distribution. Okay, that's not important right now. We're going to be using normal distribution in class. But we could find this with the binomial distribution. And my point is, if you do that, we'll see the result on the next page. What the probability is that getting 64 heads or 36 heads or farther from 50 could happen by chance for a fair coin under the conditions of the null hypothesis. So we find the probability of the latter, always the case. And when I do it with a binomial distribution, you could practice, see if you can reproduce this number on your own. For one side, it should be 0.003, but for two-sided, it should be 0.006. And this is what we're saying. If we have a fair coin, what we just observed take place, we will only observe this proportion of the time, 0.006, about 6 times in 1,000. Okay? So there are only two reasonable conclusions. Okay? Either the coin is not fair, or the coin is fair and we've observed something that's incredibly unlikely. Okay? This is so unlikely that we'll conclude the coin is not fair. We'll reject that null hypothesis that p equals 1/2. Okay? We'll say no, reject. And we'll say the probability of heads is actually different than 1/2. And the reason for doing a two-sided test instead of a one-sided test, it lowers the likelihood that you'll reject the null hypothesis when it's true. Okay, so a type of mistake you don't want to make. Okay, so I have to do a little more explanation, then we'll do some more examples. But a hypothesis test, also called a test of significance, the old term used to be hypothesis test, and it became changed over time through fashion. Okay, it starts with a hypothesis about a parameter, the null and alternative hypothesis. So the hypothesis is usually, the way it's stated here is the null hypothesis. And we have some data that seem to deviate from what we would expect if the null hypothesis were true. Okay? And then we ask the question, are the data compatible with the null hypothesis? Or are the data so strong that we're required to reject the null hypothesis in favor of some alternative hypothesis, H sub A? Okay. All right, so in example 1 above about Turkey, the parameter mu is the mean of a population. And I want to be clear that population is of students. There's also the population of everyone, okay? But we were using our sample of 25 to make conclusions about the population of students at Ankara University. And we were just assuming for our null hypothesis that that mu would be the same as the mu that we know from Wikipedia is true for all adults in Turkey. Okay. And then alternative hypothesis, we'll have to make decisions, and we'll see examples of this, whether our alternative hypothesis should be like the one in that Turkish example, or should be two-sided, like the one with the coins, okay? And I want to be clear, so not every instructor would agree with this, but I think there is a strong logical preference for two-sided tests. Whenever they make sense, they're better to do. Okay, and the data that we have is usually a simple random sample and its mean. Later in the course, we'll be dealing with simple random samples and proportions as well. All right, so the hypothesis tested is called H0 or H0. We've seen that already, and the alternative hypothesis is denoted H sub A. Some books denote it H sub 1. Okay, and often we believe the alternative hypothesis is true. But we need to conduct a test to see if our evidence is really strong enough for that. We're going to accept the null hypothesis, or I shouldn't say accept, that's 1980s terminology. We're going to fail to reject the null hypothesis unless we have strong evidence that the alternative hypothesis is true. And I want to be clear. We sometimes conclude the null hypothesis is not true. We reject it. We never consider ourselves to have proven that the null hypothesis is true. We just fail to have enough evidence to reject it. Okay, I'll talk more about that in a bit as well. Okay, so typically we suspect that the alternative hypothesis is true, as I just said, and we're just trying to see if we have enough data to really back up our intuition there. All right, so let's look back on that example with the coins again. We were interested in, is the coin fair or not? So our null hypothesis was that P, the probability of heads, is 1/2. And our alternative hypothesis, as I mentioned before, was P not equal to 1/2. So we ended up with a two-sided test. And the reason we don't take the alternative hypothesis to be greater than 1/2 is the only reason we had to do that is that our data ended up with more heads than we would expect. Using our data to inform our hypothesis, err too often in rejecting the null hypothesis. So it even has a name. Back in the day, this was called data mining, and it was a terrible thing. Now data mining is something completely different in machine learning, and a cool thing to do that pays well. So the name of this has changed to data snooping. Okay, if we let the data help us decide what the alternative hypothesis should be, we bias our inference in favor of the alternative hypothesis. That's why we don't do it. Okay, so we want to form our alternative hypothesis before looking at the data. All right. Okay, so here's a question. Here's a question of interest. Do students who place out of French 101 differ in their listening comprehension from those who take the course? Okay, when students come to UNC, some start in French 101, some who want to study French test out of French 101, and we're interested in the question, just differ. Is there a difference in the listening comprehension of those two groups? So we're going to assume that students who place out have the same listening comprehension as students who take the course, unless we have strong evidence to the contrary. And that really suggests our null and alternative hypotheses. Okay, so on a listening comprehension test, the mean score of all students who take the test is known to be 26. This is going to be, it's our mu for the broader population, the population mean. So the population we're interested in is students who place out of French 101, but we're going to assume for that group, without evidence, that their mean is the same as the mean for students who take French 101. Okay, so I haven't looked at any data so far. Hopefully we're asked for the alternative hypothesis next. The same exam is given to a simple random sample of 35 students who placed out of French 101 to see if their performance is different. So we can see now the null hypothesis. Well, perhaps there's a question on the next page. Let's just get to the next page. Okay, so here are the questions. First, what is the parameter? So the first parameter is average. I should have said mean there, but average listening comprehension score, average score for testers out of French 101. So the parameter we're looking for is mu. That's a pretty poor mu, but you get the idea. Our null hypothesis, without further information, is that mu is equal to 26. Okay, and the way the question is worded, do students who test out differ? The alternative hypothesis I can write down is that the mean for this group of students who test out is not equal to 26. Okay, and then we're asked the question, would your answer to any of these questions change if you learned that the mean score of the sample of students who placed out of French 101 was 21? And the answer is no. Okay, we didn't have a reason to think ahead of time that students scored more poorly on listening comprehension, and the way the question is worded, we're just trying to determine if their performance is different. So we definitely want a two-sided test. We can't let the data that we've collected as part of our random sample influence our alternative hypothesis. Doing so causes us to reject the null hypothesis too often. Okay. All right, so the answer to that question was no. That way. All right. So this is just a summary that when we do a hypothesis test, and we're going to talk about z-scores and z-tests in just a minute, we have an unknown population mean mu. We actually have a known population standard deviation sigma, which is awkward, but as I mentioned, we deal with that later in the course when we move from z-test to t-test. And we have a null hypothesis, like mu equals some number. Mu 0 just means some number, some constant, like 12, okay? And then we have an alternative hypothesis that can be mu greater than that 12, less than that 12, or not equal to that 12. We need to be ready to handle all three. The data that we have is x bar, the mean for a sample of size n. Okay. All right, for example, I want to test the null hypothesis that mu equals 450. okay, versus the alternative hypothesis that mu is greater than 450. And when I translated this into the presentation software, the X bar got messed up. I think that happened last time I did this as well. But I didn't notice this time until I was in the middle of the lecture. So that should be the observed value of X bar. So we have a sample of 500. The observed average for that 500 is 461. We have a population standard deviation of 100. And we want to find the p-value. I want to find the probability that a difference this large could have occurred by accident. That's called the p-value. Okay, so let me just mention that the p-value equals the probability that X bar, this the alternative hypothesis is one-sided, so it's the probability that X bar is greater than, equal, doesn't matter because it's we're using a normal distribution. We weren't told that the population was normally distributed, but since the sample size is 500, we don't need that assumption. So I want the probability that X bar is greater than 461, assuming the null hypothesis is true. What's the probability something like this happens by chance? Now I'm going to give two solutions. I'm going to give a solution we would do right now today, and then I'm going to introduce the z-score and give a solution based on the z-score, because when researchers or people doing statistics report their results and say we've rejected or not rejected, they always give the z-score as well because it gives us an immediate impression as to how extreme the data are. So first I'm just going to do what we would have done up to today. Okay, to find this probability, I would draw a curve. I know the mean is 450 under the conditions of the null hypothesis, and I want the probability, so this is X bar, the probability that X bar is greater than 461. So we know that that equals 1 minus norm.dist of 461, where the mean is 450, and the standard deviation is the standard deviation of X bar, not the standard deviation of the population random variable X. So that standard deviation for X bar is 100 over square root of 500. And then we have to write true or 1, whatever we want to put in the last spot. I put 1 there, but I've been writing true every time in class, so let me just add a true. Okay, and when I do that calculation, I get that the p-value, the probability that this would occur by chance for a random sample of 500, if the true population mean were 450, the probability that we would observe a sample mean as high as 461 is, I got 0.0069. This is a really small probability. So the idea that this happened by chance is really, really small. I'm going to reject H0. I'm going to say no. I believe the alternative hypothesis. I believe that mu is bigger than 450. I don't necessarily believe mu is 461, but I believe it's bigger than 450 because this is just too strong, too extreme a result to observe if the null hypothesis is true, if the true mean for the population is 450. Okay, I wanted to say something else there. Yeah, that'll do. Okay, so I want to introduce the idea of a z-score for these data, for this X bar. I want to find a z-score. We've seen z-score before, but not exactly in this context. And then I want to just show how to get the solution, the same solution, using a z-score. Okay, so same question, solution with z-score. So first, we have to find the z-score, okay? And we know from earlier in the class that z is always x minus mu over sigma. Okay, but we're interested in the z-score of the X bar, so I'll call that z sub X bar. Okay, and that's going to be X bar minus mu sub X bar. Okay, we know mu sub X bar is just mu. This is the mean of the sampling distribution, and I know if I take lots and lots of samples of size 500, we expect the average of those samples to be around 450. Sorry, so it's the same as mu divided by the standard deviation for X bar. I could have just written sigma sub X bar there, but I wrote sigma over root n. Okay, or SE sub X bar, whatever you like. Okay, so the z-score that we want, this is the z-score, is the X bar that we observed, 461, minus mu sub X bar, which is the same as the population mean, 450, divided by sigma, where is sigma? Sigma is 100 divided by 100 divided by the square root of 500. Okay, and if you calculate that z-score, we get 2.46. Okay, so this says our result with 461 instead of 450 is 2.46 standard deviations above the mean. We know that's an extreme number of standard deviations, so it's not shocking that we got a really small p-value. Remember, we got p equals 0.0069. And we just want to see how to get that same result with z-scores. I draw the standard normal distribution, what we call the z distribution sometimes. I know the mean is 0. I know the z-score is 2.46. And this time I could think of it as I'm trying to find the probability of obtaining a z-score that extreme, 2.46, if the null hypothesis is true. The probability of getting a sample of size 500 and getting a z-score that high, assuming the null hypothesis is true. We know how to do this. This is 1 minus norm.dist. You may know other ways to do it, but this is one way to do it. Norm.dist of 2.46, 0, 1. Whoops. Let's see if I can erase live on the fly here. I have to say, that was a pretty good erasing job. Okay, 1 and then true. True or 1, we can put whatever we want there. And if you do that, you'll get 0.0069, okay? That same p-value. Okay, and so again, because the p-value is so small, we reject H0. Now we'll talk in a minute about deciding how small a p-value causes us to reject H0. Right now, we're rejecting if the p-value is less than 0.05. It's just a rule of thumb. We have to pick a number. 0.05 is not a magical number, but it's a number commonly used. Okay, so we're 20 minutes in to this video lecture. Might be a good time for you to take a break. Go, have a responsible, age-appropriate beverage, and take a few minutes break and come back, and I'll get to the next example. Okay. All right. This page is just a summary of what we did just a few minutes ago. So I will skip over that. And so I just want to summarize. To test the hypothesis, mu equals some number. Mu equals mu0. It looks weird. I remember the first time I took statistics, I thought this looked really weird. So I'd always cross out the mu0 and write a 12. Okay, I mean, it's not always 12. Okay, the last example, it was 450, right? Okay. And we have the sample mean x bar, which the software has gotten rid of for some reason. Sample size n, and we know the population standard deviation sigma. And then we compute the standardized test statistic. That's z, okay? And z is always x bar minus mu sub x bar, but mu sub x bar is just mu. I'm just trying to write things consistently, divided by sigma sub x bar. Okay, so we solved the previous example two ways. I found the probability that x was greater than x bar, and I found the probability that z was greater than z bar. And that's if the alternative hypothesis is mu greater than mu0. Okay. For the Turkish example, our alternative hypothesis was that mu is less than mu0. So we calculated the probability that x was less than x bar, assuming the null hypothesis is true. And finally, with the coins example, we did. I didn't write it with z's, but we could talk about it with z's as well. But we had to find the probability of being on either side of x bar just being as far from the mean as we observed, assuming the null hypothesis is true. We'll be sure to do another example like this. All right, so that's where we are. Okay, so let's look at this exercise, and we're going to do it as a one-sided test and a two-sided test so we can compare the results. So we have a test. I haven't given the context here, but we're told that the null hypothesis is that mu equals 25 based on a simple random sample of size n equals 25. That 25 sneak to the next line. And we want to assume the population standard deviation is 5. Okay, so I'll do parts A and B on this slide, and then I'll do part C on the next slide, okay? First we're asked, what is the test statistic? Well, so the idea is we want to be able to say to someone quickly, what were our results like? So we like to talk in number of standard deviations, or z-score, okay? So I find z. I know z is x bar minus mu, which is the same as mu sub x bar, divided by the population standard deviation over square root of n, which in this case is square root of 25, Okay, so Z is equal to 27, our observed sample size, minus our null hypothesis value of mu, divided by the standard deviation is 5 over square root of 25, which happens to be 1. So if you work this out, you get Z equal 2. And now we know automatically, right? 2 standard deviations, we know the probability of being 2 standard deviations away. Okay, so if I want to find the p-value, I could do it directly with norm.dist with 27 and 25, but I could do the p-value, so this is B. The p-value is just the probability that we observe a z as large as 2 if the null hypothesis is true. So we draw that little standard normal distribution. We have 0, we have 2. So this is equal to 1 minus norm.dist of 2, 0, 1 true. And we already know this is around 2.5% because we know the rule of thumb for the normal distribution. But now we're becoming a little more sophisticated. We could actually calculate the number. It should be around 2.5%. In fact, the exact number is 0.0228. Pretty close to 2.5%, but not quite. Okay. So one-sided test, we would end up rejecting the null hypothesis because p is less than 0.05. We could also have found this same p-value looking at the probability that x bar is greater than 27, assuming the null hypothesis is true. And we know you could draw the picture for x bar, but that would be 1 minus norm.dist of 27, where the normal distribution has mean 25 and standard deviation sigma over root n. So that's standard deviation 5 over square root of 25. I know that's 1, but I wrote it this way so it's clear where I got it. Okay, whenever we see that x bar, we end up dividing our standard deviation by root n. You can write true or 1 here. And you get the same number, 0.0228. Okay. All right, let's take a look at part C. So part C, our alternative hypothesis is mu not equal to 25. So this is two-sided. So now we're asking, so the p-value is the probability not that we observe a z as large as, what was it, 2.4, oh, 2, it was 2. As large as 2, but as far from 0 as 2. Okay, it's a two-sided hypothesis test. Okay? And we can put less than, equal to. It's a normal distribution, so it doesn't matter. Same answer. And we already know, we've done the calculation already. We already know this is 0.0, I say I know, I have to look, 0.0228 plus normal distribution, and in particular standard normal distribution. They're symmetric, so I know if I draw the picture, so I have 0, 2, -2. My standard normal distributions are starting to look worse and worse. Okay, all right. But we know it's symmetric, so the areas have to be the same. So the area on either side is 0.0228. So for the two-sided alternative hypothesis, two-sided, we always get exactly twice the probability of what we would get for a one-sided test, as long as we're doing a z-test, where we're talking about the normal distribution, a symmetric distribution. Okay, so this turns out to be, if you do the math, right around 0.0455. Right around, we knew it was around 5%, right? Because we know for 2 standard deviations, normal distribution, we know approximately 95% is in between, but now we're using more exact numbers. That's our p-value. So you can see, since we only reject the null hypothesis if the p-value is small, it's harder to reject the null hypothesis for a two-sided test. You can see this guy barely got in under the wire. Okay, but if we're using 0.05 as our cutoff, what will be called level of significance in a minute, we would still reject since p is less than 0.05. Wow, my handwriting is deteriorating. It's because I'm trying to be careful not to put my palm on what shuts off the recording here. Okay, all right, so that's the two-sided test. All right, and there might be some summary on the next page with these answers having disappeared. All right, nope. Okay, so here's some practice with z-scores, okay, and finding p-values with z-scores. We can find them directly from the data as well, but here's just some practice. We have a hypothesis test where H0 is mu equal 46, HA is mu less than 46. Not told the sample size, not told the sample mean, but I'm told the z-score I got is -1.82, so I can find the p-value. Since it's a one-sided test, the p-value is just p equal to the probability that z is less than negative 1.82, assuming null hypothesis is true, and I can draw a picture for this. So 0, negative 1.82. I know the answer should be less than 16% because that's more than one standard deviation away. So that p-value, p, will equal norm.dist of, let's see, negative 1.82, 0, 1, true. And we'll see that number in just a minute. I don't remember what the number is. Here's a two-sided test, same thing. So when I draw the picture here, it looks the same, except now I'm interested not in the probability that z is less than negative 1.82, but the probability that z is as far from 0 as 1.82. So I need to look up here at positive 1.82 as well. And I need to consider the area to the right of positive 1.82. And I know that's just going to be, you can find it lots of ways. You can add these two, calculate these two areas separately, but the least amount of work, which is always, as mathematicians and statisticians, we want to do what takes the least amount of work. It's going to be 2 times this area to the left since the distribution is symmetric. So 2 times what we had above, norm.dist of negative 1.82, 0, 1, true. Okay, I'll summarize these answers on the next slide. And hang in there, we're approaching the end of this lecture. Okay, so that answer was 0.0344. It was less than 0.16, a lot less it turns out. And for the two-sided test, the answer was exactly twice that. So here's a good example, okay? Consider if our cutoff for rejecting the null hypothesis, if our cutoff, it's called alpha, but alpha equal 0.05. So assume 0.05 is our cutoff. If p is less than 0.05, we reject the null hypothesis. If p is greater than 0.05, we fail to reject. Okay, well, in this case, one-sided test, we would reject the null hypothesis. We would say this is not true, okay? But if we did a two-sided test, which is more appropriate, we would fail to reject. Okay, so it's a good example. It makes a difference. A two-sided test, it's harder to reject a null hypothesis for a two-sided test. Let's call that fail to reject. I'm not saying I think the null hypothesis is true. I'm just saying under the conditions of a two-sided test and this cutoff we've assigned, what will be called level of significance in a minute, alpha equal 0.05, I reject if the p-value is less than that alpha we set, okay? Under those conditions, I would fail to reject for a two-sided test. I'd say it might be less, might be different, might not, but I don't have enough evidence to reject it because I don't want to make that kind of mistake more than 5% of the time. All right, the mistake I'm talking about, I don't want to reject the null hypothesis when it's true 5% of the time, more than 5% of the time. Okay. All right, and here's just a note, but I've mentioned this already. Okay. I think I want to leave this one for you to work. Okay, so this question will be for you to work, but I want to talk about level of significance in the next couple of slides before I end this lecture, this video. But this will be for you to work. We'll look at the solution in class on Wednesday. Hopefully one of you will present. Okay. All right, so slide 20, also for you to work. So this is just, so 4, there's an O in that, for you to work. This is the second question. And I'll let you read things closely. You need to, it's in the context of a problem. You want to pick out what the parameter of interest is. What is the population we're interested in? Remember, the population is always, sort of a smaller group, okay? What are the null and alternative hypotheses? Okay, it's nice to get to use the plural of hypothesis. Okay, and what is the statistic that estimates the parameter? And finally, what is the p-value? And just for practice, why don't you also find the z-score? Because when we report results as researchers, as psychologists, biologists in the medical field, we want to report the z-score as well. The reason for that, the z-score tells us a lot more than the p-value. The p-value tells us, than the level of significance. The level of significance tells us what our cutoff should be, but the reader may be interested in knowing how close we were to that level of significance. Okay, 2 more slides. First, this statistical significance, this alpha I've been talking about, we want to answer the question, how small does the p-value need to be for us to decide to reject H0 in favor of the alternative hypothesis? And the answer is we set this number ahead of time. Common numbers to use, we haven't called it alpha every time, but we've been using a cutoff of 0.05. Okay, it's also common to use 0.01. It's common to use other numbers as well. Okay, so we're going to say, so this is an important quote because we hear the words statistically significant a lot in life. Statistically significant means the p-value is smaller than whatever cutoff we set, less than or equal to. Now we can argue about if the p-value equals alpha. That's kind of, the logical probability of that happening is 0 in life, and we shouldn't face that. But this looks like we reject if p is less than or equal to alpha. Okay, if you're reading a published report and it says a test was significant and it doesn't give a level alpha, first of all, that's poor practice, but you can usually assume that alpha is 0.05. And finally, I just want to make clear, when we report results, it's important not only to say the result was significant, but it's very important to either give the p-value or the z-score. Okay? And the reason for that is it informs your reader what the actual results of the test were, and they can decide for themselves. If you decided 0.03 is statistically significant, they may think, well, no, not for them. Really, they want p-values and alpha, a level of significance, to be 0.01 or 0.001. And the reader gets a chance to decide that for themselves. Okay, so repeating on a significance study, you must provide either alpha or p or both. I would say z or p or both. But anyway, z being the z-score. Okay, so attempt the homework and web assign. We'll discuss them as needed tomorrow.